welcome to lecture 94. So, now we are going to look into the interception problem between two vehicles in elliptical orbit. So, already we have done it for the circular orbit. So, let us start with. So, here circular orbit, elliptical orbit is given. One satellite is located at A and another satellite is located at B, and it is required that A catches B at C. A needs to catch B at C. So, angles are given in here in this case, and these angles are not equal. It may appear from the figure that it is equal, but it is not equal. So, this as usual we will show this as, let us show it outside. So, this angle is phi B C and angle between this and this is phi A B, and this is phi B C. Now, we need to send the satellite in a faster orbit. So, let us say this is the orbit that we choose, and for this orbit the perigee lies here in this position, perigee of the transfer orbit, perigee of the transfer orbit, which we can show here as theta, or this is the location of this. So, we can write this as theta A, and similarly, the location of this from this place, from this perigee, then this will be theta C. We are not worried about the theta B, because theta B does not lie on the transfer trajectory. So, this is your transfer trajectory, So, we are not worried about this. So, here theta A is not known to us. So, theta A, this is unknown, and we need to work out this quantity. So, we will write here the angles, this point is O, and perigee as it appears, it appears from this place that it is lying along this brown line, but that is not the truth. I can make it little look different. Let us say it is like this. So, this is the perigee point. Okay, so, the angle AOB, this is phi AB, angle BOC, this equal to phi BC as we have named it, and angle POA equal to theta A, angle POC equal to theta C. So, these are the angles we are taking. We will write phi equal to phi AB plus phi BC equal to angle AOC. Okay. Now, we need to recall what I have done earlier for two non-tangent bond, how the satellite orbit is to be decided, okay. The transfer trajectory is to be decided, this we have done earlier. So, that information we need to use here in this place. So, let us write 1 by r, L by r equal to 1 plus e cos theta, L by r, this equal to 1 plus e cos theta. This is the expression. So, 1 by r we write as 1 plus e cos theta divided by L. So, this L can be written in terms of h square times mu, h square divided by mu. So, mu goes to numerator. Okay. So, following this equation, then we can write R A equal to 1 by E cos theta A, E times cos theta A times mu by h square. And here one should remember that while we are using this equation, okay, and theta A we are writing. So, theta A and theta C, these quantities are defined only along the transfer trajectory. So, here we have it should be E t. Okay. So, this is E t. Similarly, we will have 1 by R c equal to 1 plus E t cos theta c mu by h square. And this quantity is nothing but 1 plus E t cos theta c. Theta c is, if you look for the angle, so theta c is theta a plus phi, as we have defined here in this place, times mu divided by h square. Or simply we can write in terms of L, it does not matter. So, therefore, R A by R c, we divide the second, let us say this is 1 and this is 2. So, divide 2 by 1 and this will yield R A by R c equal to 1 plus E t cos theta a plus phi and divided by 1 plus E t cos theta a. Now, we will look into this place. R A is the quantity which is known to us, okay, because this is defined by also where it is located with respect to the in the original trajectory. In this trajectory, where A is located, this is known to us, because that angle is given, okay, that position of that will be known to you. So, R B will also be known and R C will also be known to you, because these angles are known and therefore, it can be determined where they are located. So, we utilize all these information for solving this problem, and therefore, from here we can write, if we rearrange. So, this is R A plus R A E t cos theta a, R C E t cos theta a plus phi, and separating out E t, R A times cos theta a minus R c times cos theta a plus phi, this equal to R c minus R A, and this implies E t equal to theta a plus phi. So, now look here in this equation, it is important to discuss this. R A is known, this R A is known here, R C is known, okay. Theta a we are assuming, phi is known. Okay. So, all the quantities on the right hand side in this equation, it is known. So, this side is known, and therefore, this yields you. So, this gives E t. Now, we can proceed to work. So, once E t is known and we have assumed already the position theta a is assumed. So, therefore, E t is known and rest others R v a square by mu as we were discussing earlier. So, it can be computed. So, this is 1 2 and let us say this equation is 3. Now, steps to be carried out. Assume theta a and for known phi is known as this written earlier, and for known phi obtain E t using equation 3. This is the first step. Now, for known theta a already we have assumed. So, theta a, phi and E t, compute R a V a square divided by mu and R a R c V c square divided by mu and the corresponding angle where it is located. So, this is suppose theta, okay, and this is the trajectory to this is v, this we can say this is alpha, this is the flight path angle phi, this is v and this is the r direction r cap, this is theta direction, this is theta cap. Okay. So, we need to calculate all these things, alpha a at the point A and alpha c. Okay. Using equation which equation we have to use, already I have mentioned R b a square divided by mu to 1 plus 2 e cos theta plus E a square divided by 1 plus E cos theta. This we need to use, where theta appears as the true anomaly. And here tan tan alpha we want to decide, alpha we want to write. Okay. So, see alpha I have written from this point, somewhere it may be also, if this is the v direction, I have written alpha from here, alpha can be, okay, let me draw it little properly. So, this is the v direction, this I have shown as alpha, but alpha can be measured from the horizontal also. Okay. That means, alpha I can take from this place to this place, but this I am not taking throughout, perhaps as far as I remember I have used with respect to this I have decided as the alpha angle. Okay. So, this I have always taken as the alpha angle. Okay. So, we have to be careful about this. So, tan phi by 2 plus alpha, this will be given by minus E sin theta. Look back into the equation we have derived, E cos theta minus E sin theta divided by 1 plus E cos theta by 2 plus. Okay. So, from this place we get cot alpha equal to E sin theta divided by 1 plus E cos theta. Okay. So, cot alpha we have written like this. So, here phi equal to this angle is phi. So, phi equal to pi by 2 minus alpha. Okay. So, cot pi by 2 minus alpha. Okay. Alpha becomes pi by 2 minus phi. So, we write here in terms of phi. Pi by 2 minus phi equal to E sin theta plus 1 by E cos theta, or equally we can write here tan phi as we have written earlier. So, this equation needs to be used whenever required. Rest r dot and other things already I have written. Okay. So, this is a step number 2. Find A equal to plus minus r by r b square by mu minus 2, or 2 minus, whatever the way you write, we can write here minus plus, or r by 2 minus r b square divided by mu, both can be written here. Once we write plus minus, so irrespective of either I write 2 first or the r b square by mu first, it does not matter. So, we have to choose it properly. Calculate T A. Now, here in this case, because it is elliptical orbit, so we need to calculate T A and T C separately, and T C we need to calculate it separately, and from there find TAC transfer, and this is to be done in the transfer orbit. TAC transfer will be TC minus TA in the transfer orbit. Then compare TAC transfer with TBC in the actual orbit. This is in the original orbit. If this is equal, so your job is done. If not, then we have to repeat from step 1. Repeat until the 2 times match. Okay, so this is the process involved. Now, based on this, I will take the case of a non-coplanar orbit problem, and because non-coplanar orbit or planar orbit, it does not matter much, it's the process is the same. So, I will solve one problem based on this. rendezvous between two vehicles in non-coplanar orbit. So, here in this case and I can compose this problem in multiple ways. Okay. So, say this is your polar orbit, and here we write z, this is x and this is y. This is point B and here some point is C. This is point C, whose latitude is 30 degree. This is 30-degree angle. Radius of this circle is 2.5 r earth. So, r earth I will simply write as 2.r, radius of earth. So, problem it states like this. I will have to write the problem here, and let us consider another orbit whose perigee lies on the z axis and at a distance 1.5 r. Okay. And from here, so this is originally an elliptical orbit lying in the xy plane. Okay. So, this is an elliptical orbit lying in the xy plane, xz plane. Okay. So, this we call as the equatorial orbit. So, this is your equatorial orbit lying in xz plane, and this is lying in polar orbit in the xy plane. So, quickly I write the statement for this. Consider a vehicle in a polar orbit or in a circular polar orbit lying in xy plane x axis lies in the equatorial plane. Consider a vehicle, we name this vehicle, let us name this vehicle as V. Consider a vehicle V. So, but you will get confused. We write this as satellites. So, let at any instant or let at any time the vehicle is be located at point B in the equatorial plane. So, your vehicle S is lying here at point B, and what is to be done, that another satellite which is moving in this equatorial orbit. So, here this is its perigee position, and this position we are writing as A. Okay. So, we have to decide an orbit such that if I give impulse along this orbit at point A, so it goes and catches B at C. So, this is what is required, it goes and catches B at C. So, given position of S at t equal to 0 to be R b equal to 2.5 r, where r is the radius of earth as written here. Consider another vehicle lying in an equatorial elliptical orbit of eccentricity. So, this is the circular orbit and this is your elliptical orbit of eccentricity equal to 0.5 with perigee located at A on the z axis. And given that when the other vehicle is at B, the vehicle at A is given an impulse or impulsive velocity so that it catches B at C, where R A is given to be 1.5 r. So, C latitude is given to be 30 degree. So, this is the information, and you have to decide how much impulse needs to be given at A, such that the vehicle at A will go and catch the vehicle this S at the point C. This is the objective. So, we will continue in the next lecture. I have stated the problem. Thank you very much.